Chapter 17, Reaction Kinetics. In this chapter, we're going to be talking about how reactions actually take place. How do atoms and molecules get changed from one substance into another substance? So to begin this, where we're going to learn about the reaction process, let's just take an example and start thinking through this step by step. What's possibly happening down on the atom or molecule level? And let's begin with this reaction here where we have a hydrogen molecule reacting with an iodine molecule and ending up with two hydrogen iodide molecules. And what we do know is this doesn't occur in just a single step. So if it doesn't occur in a single step, then what are the possible steps that it could go through? So let's think about what are the possible stepwise reactions that could actually occur. Well, we first of all could have the hydrogen molecule somehow breaking apart and becoming two separate hydrogen atoms. And then we could have these two hydrogen atoms colliding with the iodine molecule. Maybe you could picture it maybe like one hitting from one side, one hitting from the other side of the iodine molecule, and then the iodine molecule splitting in two, and you have two hydrogen iodide molecules. Maybe another way that this could be happening is it begins with the iodine molecule breaking something, causing it to break apart into two separate iodine atoms. And these two iodine atoms happen to hit a hydrogen molecule, maybe one from either side, kind of like a pattern similar to the first one that we talked about. And the hydrogen splits in half, and now I have two hydrogen iodide molecules. Or a third way, maybe the iodine molecule breaks apart into two separate iodine atoms, kind of like in our second example, and then the hydrogen molecule collides with one of these atoms, and in the process of doing it, the hydrogen molecule splits and one of the hydrogen goes off by itself and the other hydrogen bonds to the iodine. So we have a hydrogen iodide and now a hydrogen atom that was produced. And then maybe that hydrogen atom finds the iodine atom that hasn't been used, the other iodine atom, and forms another molecule of hydrogen iodide. So, here's just different ways of visioning that this could possibly happen. But which of these is correct, or are any of these correct? So what we want to accomplish in this first section is we're going to explain the concept of reaction mechanism. We're going to use the collision theory to interpret chemical reaction. We're also going to be defining a term called the activated complex, and then we're going to talk about the energy that it takes for a reaction to occur, activation energy. Now, chemists have found that chemical reactions occur at widely differing rates. You have things that happen very slowly, like iron rusting, to the chemical reaction in dynamite going off. So we have just a very wide range of rates that these chemical reactions can occur at. Now, the speed of a chemical reaction depends on the energy pathway that a reaction follows. Now, we may not understand what that reaction or that energy pathway is yet, but through the course of this chapter, hopefully we'll better understand that. And the speed also depends on the changes that take place on the molecular level when these substances actually react with each other. So some reactions have intermediate steps, kind of like what we did in our thought problem at the beginning. There were things that that came into existence and then ceased to exist by the time we got to the very end. So we would call those intermediate steps. Now, so only ions and molecules with very high energy can overcome the repulsive forces and get close enough to react. So the understanding is that for two molecules to react with each other, they have to approach each other with a high enough speed that their energy is enough to overcome the repulsive forces of their electron clouds. Remember, both of their electron clouds on the outside should repel each other. So we have to have them traveling toward each other at a high enough speed with enough energy so that they can overcome their repulsion and get their electron clouds close enough together so that they can start interacting with each other. Now, chemical equations describe the reaction. You know, we've written all kinds of chemical equations and we've balanced them, but they don't show the reaction mechanism. In other words, how do they actually get changed from reactants into products? And let's take this example right here that was we've been talking about at the very beginning. Here we have a hydrogen molecule reacting with an iodine molecule and forming two hydrogen iodide molecules. It doesn't say how that happens. Now the reaction mechanism is going to be this step-by-step sequence of events of that reaction, and this is going to produce this overall reaction at the very end. And this is sort of similar to something that we've had before where we had spectator ions that we would cross out and then we'd have the overall reaction. We're going to be using an idea that's similar to that. So experiments can often be designed that suggest the probable sequence of steps in a reaction mechanism. So to understand these steps, there's nothing obvious about them that screams how this is happening. We have to design experiments that we can reveal if this intermediate step or like for instance the two separate iodine atoms or the two separate hydrogen atoms, maybe we can design an experiment in such a way that if they actually occur, that something else will be formed or something like that. So experiments is how they have come about learning all these things. There's nothing about the reaction that tells us how this should occur, and sometimes we're in for surprises. Now, a reaction that appears from its balanced equation to be a simple process may actually be the result of several simple steps. And if you think back to what we had before, we had some things formed along the way where we had iodide ions, and then we had this H2I strange looking molecule forming. They don't appear in the final equation. So those would be these intermediate products that we have along the way. So these species that appear in some steps but not in the net equation are called intermediates. So the iodide ion and this H2I molecule is going to be are called intermediates. They're there for a little while, sometimes just very briefly, and then by the time the reaction has completed, they no longer exist. So they're just like temporary structures. So let's look at our the formation of those hydrogen iodide like we had at the beginning. Let's go back to that again. And let's look at one of the ways that we talked about. One of the ways we said is that the iodine molecule that we have here in step one, this iodine molecule right here, is breaking apart to form two iodine atoms, not ions, but atoms. And then in the second step, we have these two iodine atoms colliding with the hydrogen molecule right here and ending up forming two hydrogen iodide molecules. So that's one way that this could possibly happen. Let's look at another one that we talked about. That was kind of like I think the third process that we talked about. Is the first step is similar to the one we have over here on the left, where we have a iodine molecule breaking apart to form two iodine atoms, and then one of those iodine atoms hits the hydrogen molecule and forms this intermediate right here. That's I'm not sure how you'd name it. It's not quite like a hydrogen iodide, but it's a H2I molecule. And then in a third step, the other iodine, this is not the same iodine atom as that. This is a different iodine atom. The other one strikes this intermediate structure and causes it to break apart in such a way that we end up with two separate hydrogen iodide molecules. Now, if I add these up and cross out the things that we have from one side to the other, we have the same overall reaction, I2 plus H2 forming 2HI. So to get that, we'd have to cross out the 2I on both sides of the example on the left. And because they're on opposite sides, we can cancel them out. And then when we add them together, we get that. On the right side, we can cross out the 2I with one I in step 2 and one I in step 3. And when we add them together, we still have the same reaction. And then we can also cross out the H2I on both sides. And what we have left is the I2 plus H2 equal to or forms 2HI. So this reaction has two intermediates that don't appear in our net equation. The bottom equation that we have right here, this one right here, and this one right here are called net equations. We've had that before. And the I and the H2I don't appear in them. So we call those reaction intermediates. One term that we need to define before we go on to make us so that we can understand this maybe a bit better is a homogeneous reaction is one in which the reaction occurs in such that the reactant and the products are both in the same physical state or same single phase is be another way of saying that. In other words, they're either both gases or they're both liquids. Probably the one with both gases is probably the easier one to understand. So to understand how a chemical reaction occurs, we need to think of this idea that these molecules are actually colliding with each other, and they have to collide in such a way that hard enough so that they have the right amount of energy, and they have to hit each other in the right orientation. That's not so much at the angle that they strike each other, but you have to think of the molecule as being a three-dimensional object that is also rotating. So as this molecule, let's say of a gas, is moving through the air, it's just not a stationary molecule. In other words, it just doesn't rotate or spin or anything and goes through the air. It's actually spinning at different speeds from one time to the next as it moves through the air. So in order for this reaction to occur between these substances, these particles have to collide with each other. And we have a set of assumptions that we will use to help us understand these reaction process. And these assumptions have to do with how they collide and then how do they react. And this set of assumptions is called the collision theory. So the collision theory is very important to our understanding how molecules react with each other to form products. The reactant molecules must collide with a favorable orientation, and we'll talk about that a little bit more so you can understand what we mean by that, and with enough energy. In other words, they have to hit hard enough. They both have to be moving fast enough to merge their valence electrons. Remember, those are the electrons on the outside, and we want them to get close enough to each other so that they can disrupt each other's bonds and allow new bonds to form to make the new products. So here is a picture that will kind of help us better understand the concept of orientation. At the left, we have two molecules of AB, and the B is the bigger blue ball, and the A is the little orangey brown ball on the end. And they are moving, and that's the dotted line represents the direction of their travel. They're not moving very fast, is what they're trying to show you by the small dotted lines. They're not moving very fast, and then at a point here in the middle, they collide with each other. Okay, and after the collision, they both go on their merry way without anything having happened. So here, the orientation could possibly have been correct. We're not sure yet because we haven't talked about that, but they haven't hit hard enough to get their electron clouds, their valence electrons, close enough to each other to react. In the middle diagram, they have these two molecules of AB are moving much faster, so thus they have the darker dashed red line, meaning that they are moving much faster, and they collide with each other and bounce off again with no reaction. And here they're maybe hitting hard enough to get them to react, but the atoms that need to interact are not on the right side of the, or all the atoms that need to react are not on the right side of the atom. Let's say those two little orangey brown balls on the end need to be right next to each other. Well, as you can see, they're not. They're on opposite sides. This one's on the left side pointing away in this direction, and this is on the bottom pointing in this direction. They're not near each other when they collide to allow their electron clouds, their valence electrons, to interact. And so thus they just bounce off and go on their merry way as well. Over on the right, where we have both things going for us. They're moving fast enough to collide to allow them to react, and these two that apparently need to be right next to each other are oriented in such a way that their electron clouds, their valence electrons, can actually interact with each other and bond to each other. And so as a result, down here on the bottom, we see the A molecule forming, and then we have the B as separate atoms moving off on their way. So we had a chemical reaction between A and B, and so it'd be like AB plus AB, and when we're all done, we have A2 plus two B's. So a chemical reaction produces new bonds and that are formed between specific atoms in that colliding molecule. In our previous example, it was those two small orangey brown balls that bonded to each other, and we had to break the bond between the A and the B of each original molecule. So we had some molecules breaking bonds, and we had some new bonds being formed. Now, unless the collision brings the correct atoms close together, that's the reason why we had three different pictures there, close together and in the proper orientation, the molecules will not react. So that's one of the reasons why all reactions don't occur at the same rate, because the orientations are rather random. So just to kind of review again, for the hydrogen iodide molecule to be formed or to react, we needed to have the iodides next to each other and the hydrogen, the little blue balls in this example, next to each other. In all the other examples that they show you here, the four others, their orientation is not favorable. In one of them, we have the two blue balls next to each other, but the purple ones are not next to each other in this bottom example on the left. So in all of these, the orientation was not favorable for a chemical reaction. In other words, we say the collision wasn't effective. No products are being formed. So let's kind of summarize what we've talked about yet. Collision theory provides two reasons why a collision between reactant molecules may fail to produce a new chemical species. Why won't they react? And the two reasons are: the collision is not energetic enough to supply the required energy. Both molecules are not moving fast enough, or they don't hit each other with enough speed to get the reaction to occur. They can't get their electron clouds close enough. Or when they do collide, they're not oriented in a way that enables the atoms that need to react with each other. They're not next to each other, and so the reaction won't occur. So these are going to be the two things that are going to drive much of what we're talking about as we continue on studying the reaction process. So we have the collision theory, which explains why reactions occur, and then we have these two reasons why they might not react every time they collide. And that's the end of our section for today.